So as promised, we're discussing p-series. And a p-series is a series of the form that I've written down here. The sum from n equal 1 to infinity of 1 over n to the power p. That's where the name comes from. Where p is a positive constant. So it'll be a series that'll look like 1 over 1 to the p power, plus 1 over 2 to the p power, plus 1 over 3 to the p power. So if p was 2, it'd be 1 over 1 squared, plus 1 over 2 squared, plus 1 over 3 squared. The p is the constant. Okay. Now, when p is equal to 1, as I'm saying, when p is equal to 1, it's called a harmonic series. It's a p-series where p is 1. And this harmonic series then would be the sum from n equal 1 to infinity of just 1 over n to the first power, or just 1 over n. And that would look like 1 plus 1 half plus 1 third plus 1 fourth, and so on forever. Now, the integral test will tell us some things, okay? In the case of these series, and we define f of x as 1 over x to the p power, then the hypothesis of the integral test applies. You could verify that. So that tells us that the series of 1 over n to the p converges if the integral from 1 to infinity of 1 over x to the p converges, and likewise for divergence. Now, we've discussed this before when we talked about improper integrals. So let me remind you. When we looked at these improper integrals, and we looked at an integral of the form from 1 to infinity of 1 over x to the p power, we found out that that integral had a value of 1 over p minus 1, provided p was a number bigger than 1. That would mean we have convergence. Okay, so this integral converges whenever p is greater than 1, and this integral diverges whenever p is between 0 and 1 and including 1. So if p is equal to 1, then the integral diverges as well. So here's our conclusion for a p-series. Here's the conclusion, that the sum from n equal 1 to infinity of a 1 over n to the p power. So when we're talking about a p-series, this series will converge if p is greater than 1, and it diverges if p is less than or equal to 1. And remember, in the very beginning up here, we said that the p value is a positive constant, so we don't need to say greater than 0. Okay. Okay, but we do need to know that p is, in fact, positive, greater than 0. Okay. Now, be careful. Above, for the integral, we found out that the integral converges to 1 over p minus 1. But remember, the integral test just says if converge, then converge. It doesn't say if it converges to the number that they converge to the same number. So in a p-series, all we know is about its convergence. We don't know what it converges to, or we know about its divergence. But this is a critical issue from here through the rest of the course. Okay? That's very important for us to have that in our mind when a p-series converges and when it diverges. On the next page, we'll look at a few quick examples. Okay, so for the first series, which is a harmonic series, okay, the sum from n equal 1 to infinity of 1 over n. The first thing we need to recognize that it is a p-series. And it's a p-series where p is equal to 1, right? It's n to the first power. And when p is 1 or less, 1 or less, then the p-series diverges. And so this harmonic series, or this p-series, diverges. And I mentioned that a long time ago when we first started talking about series, but here we have it in a little different setting. Okay, second one, the sum from n equal 1 to infinity of 1 over n squared. Well, once again, we need to recognize that it's a p-series. It's 1 over n to a power. It's a p-series. In this case, p is the exponent 2. And if p is greater than 1, which it is in this case, then the series converges. We don't know what it converges to, but it converges. Okay, let's look at a third one. The sum from n equal 1 to infinity of 1 over n times the square root of n. Now, here's a case that we might not recognize that this is a p-series, but let's look at this denominator, n times the square root of n. That's the same thing as n times n to the 1/2 power, and that's n to the power 3/2. So, oh, it's disguised. This is a p-series where p is equal to 3/2. And that p-value is greater than 1. And so this p-series converges. Okay, let's look at this one. The sum from n equal 4 to infinity of 1 over n minus 1 squared. Well, here we have these same kinds of problems that we don't recognize right away, and that's understandable. We don't recognize this right away, but it kind of looks like a p-series, but obviously things are not quite the same. So when n is equal to 4, we'd actually have 1 over 4 minus 1 squared, or 1 over 3 squared, wouldn't we? Plus, then we'd make n be 5, and when n is 5, we'd have 1 over 4 squared. 5 minus 1 is 4, so 1 over 4 squared. And then as n increases, you see we'd get 1 over 5 squared, and this would continue. So this is actually the tail of a p-series, isn't it? And a tail and the series itself converge or diverge correspondingly. So we're dealing with a p-series, or the tail of a p-series, where the p-value is 2. And since it's just a tail, we know the p-series itself would converge, and so the tail of the p-series that this looks like also converges. Well, that ends the issues about the integral test and p-series, and something that we're going to add to this in another lecture is going to be how we can estimate the value of a series, a positive base series, okay, that converges. And so we'll continue that in a different lecture.